Hello and welcome to this course. I am Dr. Sriram Kumar. Today we are going to learn chemical vapor deposition technique. Chemical vapor deposition technique is a very powerful tool to deposit thin film. So in chemical vapor deposition technique, let's understand what is the structure of or design of this instrument, and later on we will understand what is the effect of temperature and the pressure on the deposition and the thin film formation. In chemical vapor deposition technique, we have one closed chamber, and and this chamber has connected with the precursors container. So here we have precursors container, and so from the precursor containers there is vapor of that precursors comes out. So these vapors maybe come out because of the heating surrounding these precursors container, so that there is the formation of the vapor, and the vapors comes out from this container, and actual this vapors is carried out carried by the carrier gas, because here this vapor has not enough densities to move from here to the inside the chamber, so that we need some kind of the external carrier gases which can take this vapor, the precursors vapor, from the tube to inside the container or inside deposition chamber. So in the deposition chamber, we have this heating. That depends on the kind of the CVD technique we are going to use. So in the chemical vapor deposition technique, the normal temperature is from 600 degrees Celsius to maybe 800 degrees Celsius. So here inside the chamber, if that vapors comes in the chamber, you have the substrate there, and that gas gets physically absorbed on the surface, and because of the heating, this, for example, you have used silicon hydride. So if you heat this substrate, what happens, there is the formation of is silicon, or maybe if you use the oxygen there, then you will have the silicon dioxide. So it depends on which kind of the gas mixture you have used. If you use the inert gas there, then you only have the silicon. But if you have the here in the carrier gas, if you have the some amount of oxygen, in that case you will get the silicon dioxide deposition. So here we have the precursor, we have the carrier gas, and we have the deposition chamber. And once there is a deposition happens, we get the exhaust gas, and in that exhaust gas, maybe there is this toxic gases may be present, or toxic elements may be present. For example, in some case you will get the HF, in some case you will get the HCl. So we need to remove that toxic chemical from that uh, gas. So here we can use exhaust scrubber. So using the exhaust scrubber here, we can remove this kind of the toxic element from that gas before releasing this gas in the atmosphere. So these are the key element in the chemical vapor deposition technique. So in this technique, we have substrate material, we have the substrate temperature, at what temperature that works, composition of the reaction gas mixtures, and the pressure of the gas flow. So they are the four essential elements in chemical vapor deposition techniques. Now let's understand what are the key steps in the chemical vapor deposition technique. As I explained you, in this particular technique, we have here the precursor, and this precursor should come from this precursor container from here to there, right? So for that, we need some kind of the carrier gases. So here the first step is about transporting of that carrier gas from this container to the reaction chamber. So that is about the transport of the reactants by the forced convection. So we are putting the external pressure from that carrier gas, so that that carries that precursor vapor that from these containers to the reaction chamber. And the second step is about the diffusion. So here you have the substrate here, and your gas is passing from here to this direction. So that gaseous molecule should diffuse from that linear movement to the substrate. So this is about the diffusion of the gas towards the our substrate materials on towards the vapor. And the third step is about the absorption of the that precursors vapor on the substrate. So third step is about the absorption of material. And the fourth step is about the some kind of the surface processes. For example, there may be the chemical decomposition happens, as I explained to you. If we have this one, silicon dihydride, so that forms the silicon. Or maybe if you have add the oxygen there, so there may be the form oxygen in the carrier gas industry. In that case, you will have the silicon dioxide. So it depends on kind of the chemical decomposition happens of this precursors gas, of the sample. And there is the other kind of reactions happen, that is the surface migrations, site introduction, and others kind of the reactions. And here the fifth step. So once you have the absorption happens and the such kind of the surface reactions happens, after that you have desorption. So here the desorption is desirable by the byproducts, not the actual material that is absorbed on the surface. So here the desorption happens because you have such kind of the byproduct formations. So that should be come out from the surface. And the sixth step is about the transport of the byproducts through the boundary layer. And the seventh is about the transporting the bilayer away from the deposition region. And so from here to there by transportation happens. And after then we have the scrubber here, so that remove the toxic elements from the exhaust gas. So these are the 7 key steps in the CVD technique. Now let's understand some mechanism. What kind of the mechanism we need to follow? What is happening in the CVD chamber? So as we understand that, so first step is about the forced convection from the precursors containers to the deposition chamber, and second is about the diffusions, right? So you have the substrate here, and here the gaseous molecule SiH4 is coming from that that direction. This is moving in this direction, and you have the substrate here, silicon vapor. So that should be diffused from this way to the surface of your silicon vapor. So we can explain that flux is coming towards the surface using Fick's first law of diffusion. So so these equations about the Fick's first law of diffusion. So using Fick's first law of diffusion, we can explain what is happening on the surface. So here J1 is flux of that precursors molecule of vapor on the surface, and the D is the diffusion coefficient or the diffusivity, and the delta C by delta X is the concentration gradient. So here we can define this one. So here we can use that D to del Z. So we have the del Z diffusivity of the reactant gas, and here delta is the boundary layer thickness. Here you have your silicon wafer, and gaseous molecules coming and depositing on the surface. So the from here to there, so you have the such kind of the boundary condition, and there is the delta. So here that is the diffusion coefficient of the gas, and here this is the boundary thickness, and here Cg is the reactant concentration in the bulk, and Cs the concentration of that precursor at the surface. So here Hg is equal to dg by del, and that is called the mass transfer coefficient. So the flux is equal to Hg, mass transfer coefficient, into concentration in the bulk minus concentration at the surface. So based on that, we will define what is the flux is coming on the surface. And we have the other things happening at the step 4. There are some kind of the chemical reaction is happening, and that is the thermochemical decomposition of this material. So here at the step 4, some, for example, SiH4 is decomposing, right? So we need to know what is the kinetics of the decomposition of this material. So for that, we will explain that kinetics in terms of the flux here. So here the flux, the reactant as it reacts is equal to Ks and the Cs, where the Ks is the rate constant of this reaction. So this is the Ks, and Cs is the concentration of that reactant at the surface. So we have the two kinds of the flux. One is from the bulk to the surface. The gaseous molecules is coming from the bulk to the surface. And second is the flux of the reactions. So at the steady state current, or if we compare the rate of the flux in first and the second, so in this case we have the some kind of the rate limiting conditions here. So in this case, we have the J2 is much less than J1, because the reaction at the interface is much small, much less as compared to the flux of the gaseous molecules from the bulk to the interface. So in this case, J2 will be rate limiting. So at this particular conditions, we will have the such kind of the steady state conditions, and for that we will have overall the rate of the reactions is limited by the J2, and in that condition we have the J1 is equal to J2, and that is the steady state flux at that particular conditions. And for that, if we want to calculate what is the surface concentration, that based on rate constant. So from here we will have J1 is equal to J2, and from J1 we will have Hg, and we have Cg minus Cs, right? And from J2 we have Ks and Cs. So, and if you want to calculate Cs, so let us divide Cs on both sides. So we will have the Cg minus Cs minus 1 is equal to Ks upon Hg, right? So I divided both sides by the Cs. So this happens, and I put this one to this side. So we have the Ks by Hg. So now we will have Cg by Cs is equal to this minus 1 will come to this side, and so that will be the Ks by Hg plus 1, and that is Ks plus Hg by Hg. And finally, we will have Cs. So this is Cg by Cs, and finally we have Cs is equal to, we will have Cg Hg upon Ks plus Hg. So this is our desired concentration of the reactant at the interface, where concentration at the surface is based on what is the concentration of that gas in the bulk and what is the Hg. And here the Hg is equal to dg upon del. So here this del is boundary conditions. So boundary condition thickness and del G is the diffusion coefficient. So here Hg is the mass transfer coefficient. Now let's understand other thing is the what is the rate of the reaction. So further we have here the Cs. So we got the Cs, and at the steady state condition we have J1 is equal to J2 is equal to Js. So in this case we have Js is equal to Ks and Cs, right? And from this, okay. So from above equation we have Ks into Cg into Hg, and we have Ks plus Hg. So we have this term for the Cs. So now let's put some equivalent point here. Now here, if we just remove, take out this one, Cs outside, so what happens? We will have Hg, Ks upon here, Ks plus Hg. And that is multiplied by the Cg. So here CSS and JSS we can write here. So this term we can write as this KT, and we have the Cg. So here overall the flux at the steady state is equal to the KT and the Cs, and where KT is equal to this term, where KT is this term, right? So this is about the flux of the reactant molecule on the surface. And once we have the flux, so we can define the deposition rate, and that deposition rate is equal to the flux divided by the number of atoms per centimeter cube. So here, based on this one, so here the JSS, so we have here the JSS, so here the rate is equal to JSS divided by N, and we have here KT divided by N and the CG. And here the CG, and here we can write as the KT divided by N is and the Cg we can write as the Pg divided by KT. So from ideal gas equation we can write concentration in terms of the pressure and the Boltzmann constant and the temperature. So we have overall the deposition rate that depends on the KT and partial pressure of precursors in the reaction chamber. So this is all about how the deposition rate varies with the partial pressures. Now let's understand the conditions. So we will have these two conditions. Let's understand we have this one is the rate, deposition rate, where we have the KT. So in this particular constant, we have this two condition. First condition is about if we have Ks is greater than Hg. So this is about the surface reaction. The risk constant for the surface reaction is much faster as compared to diffusion of the precursor from bulk to the interface. That means here you have surface, right? And here the reaction. So here the conversion of this one in the silicon is much faster, and the rate constant for this process is Ks, it is much faster as compared to the diffusion of this one from surface to that one. So in that case, we will have the condition, and if we solve this one, then we will get close to the Hg, and this is the diffusion control process. So in this case, we have diffusion control. control process. And in the second case, if we have, so this surface can, that constant is much less than the Hg. So in this case, if Ks is much less than Hg, so in this case, we have Kt is close to this Ks, and in this case, so what happening here, in this particular case, your surface reaction at the surface is much less as compared to the diffusion from here bulk to the interface. So in this case, this reaction is called reaction control. Reactions control. Right. So these are the things we need to understand if you want to know what is condition in the term of the thin film formation. So we understand two cases. We have the diffusion control process, and one we have the reaction control process. And third point is we need to understand about the partial pressure. Here the rate constant. So here the deposition rate is proportional to the partial pressure. So now let's understand what is effect of partial pressure here. So suppose we have here precursors container, right? We have the precursors container. From that precursor container precursor vapor is coming, and from this we have kind of carrier gas. And here we have this tubing here where we have, if we have the high partial pressure of PZ, or maybe in this in this particular container we have the reaction chamber. If we have too much pressures inside here, so in this case, if we have this too much partial pressure, what happens? So there is the possibility about homogeneous reactions happen. So if too much pressure is there, so there may be the gaseous molecules in the homogeneous condition where the gaseous phase that reacts. So in that case, you have vapor here, and gaseous molecules is reacting in the gaseous phase only. So what happens if after the reaction in the gaseous phase, you will get some kind of the powder formation, and that powder formation will get deposited on the surface. So in that case, the surface is not homogeneously deposited, and we don't want that kind of the homogeneous reaction in the gaseous phase. We want such kind of the heterogeneous reactions. Heterogeneous reactions means we have here surface, and we want some of here the cursor is absorbed on the surface, and if we apply the temperature, so this should be decomposed and forms that nanoparticle, maybe silicon nanoparticle here. So we need such kind of the heterogeneous system. So gaseous molecules should decompose on this solid surface. We don't need such kind of the homogeneous reactions. At the same time, if we think about here, we need to think about the mean free path. So here mean free path is inversely proportional to the pressure. So if we have those high pressure, that means the mean free path is much less. In that case, there is a much chance of the collisions in the gaseous phase as compared to the absorption of that molecule at the interface. So, but at the very low pressure, what happens? Mean free path is higher. In that case, there is chance of coming this material on the surface substrate, and we will get the heterogeneous kind of the reactions. We don't need this kind of homogeneous reactions. We need heterogeneous reaction. So that is the desirable process in chemical vapor deposition system. So we understand till now we have the two kind of the conditions: diffusion control process, reaction control process. and the effect of the partial pressure on the reactions, kind of the reactions. So we need to put that partial pressure at very low so that we will increase the heterogeneous reactions, not the homogeneous kind of the reactions. Now let's understand what is effect of temperature in CVD. As we explained earlier that the overall Ks or the decomposition is much less than the Hg. So that means here the kinetics of decomposition is much lower. So in that case, the activation energy of the chemical reaction, decomposition of the chemical reaction, we have the surface. If we have the silicon surface, at decomposition at the surface of SiH4 to silicon, it has more activation energy as compared to diffusion of a diffusion. So if SiH4, diffusion from bulk to the surface. So in this case, if you have the higher activation energy, so according to Arrhenius equation, K is equal to A to the power minus E A by RT. So in this expression, this activation, so here E is activation energy. If we have the high activation energy, so in that particular case, the rate constant is highly dependent on temperature. Right. So if you increase very high temperature, so in that case, since this one, so here the EA is very high for the chemical reactions. So for that case, at very high temperature, we have the Kas is much, much higher than Hg. And that is the case of the diffusion limited condition or diffusion control process. And again, at the very low temperature, the K's surface reaction is much less than the diffusion of a species. In that case, we have the reaction limited conditions. So at high temperature, we have diffusion control process, and low temperature, we have the kinetic control process or the reaction control process. At the same time, here that diffusion has dependency. So here that dependency on T to the power 3 by 2. And at the same time, that depends on the Pg by Pt. So here that diffusion is depends on the T to the power 3 by 2. And from the RNA equation, we understand and how the activation energy plays the key role in making the reaction either the diffusion control process or the reaction control process. So this is the effect of the temperature. So now let's understand if you want to monitor the deposition rate and 1 by temperature, so 1000 by T, so that is the inverse of the temperature. So here this side we have the lower temperature, right? We have here low temperature and here we have the high temperature because this is 1 by T. So at very low temperature, what happening up to this region here. So in this particular region, we have linear relation with. So here we have we increase the temperature, what happening? There is the increase in the deposition rate, and that's why this is called the reaction control process. So in particular case, there is too much dependency, so high dependency on temperature of the deposition rate. And at the high temperature, what happening? So this reaction control process becomes here the diffusion control process where there is no dependency on temperature on the deposition rate. And so in particular case, we cannot control based on the what is the temperature of that deposition. And that is the effect of that deposition. Now let's understand based on the diffusion control process and the reaction control process, how we are going to design CVD chamber. So for that, we will have for the reaction control and so for this one, we will have the reaction control regime. So for this one, so since this deposition is very high, very much sensitive to the temperature. So for that, we need to design such kind of the chamber which has uniform temperature and the control. So if we have the control over the temperature and the uniformity, then by controlling these two parameters, we can control the depo deposition of this material in this particular syringe. We have the another reason, that is the diffusion control process. So in that diffusion control process, that deposition is very much sensitive to this pressure. As we know here, the dz is also that proportional to the pg upon the pt. So if we control the overall the total pressure, so by controlling this to overall the total pressure, we can control the diffusion, and based on that, we will have the control over the deposition. So in the diffusion control process, we can have such kind of design where we have the uniform flow of the precursors on the substrate. So now let's understand how we'll design the reaction control CVD chamber. So in this particular chamber, since this is very high dependency on, in particular condition, deposition very much dependent on temperature. So for that, we need to develop such kind of the chamber where we'll have the such kind of the heating. So there will be the heating coil around the deposition chamber, so that we will have the uniform temperature around inside the chamber, so that we will get the uniform deposition. So if we have the heating coil around the chamber, so in the particular case, we have this deposition on the wall of the container as well. So to eliminate contamination from one material to the another, we need to use separate container for different kind of the material in this reaction control CVD chamber. And in diffusion control CVD chamber, since this kind of deposition depends on pressure as compared to the on temperature, so in this case we can use here this cool wall system. So here we don't have some kind of this coiling as heating coil around the deposition chamber, but here we have some kind of the inclined sample here. Suppose if you have this chamber, and if you use a flat surface, maybe if you have this kind of the flat, and if you just flow the air or the precursors, what happens? There may be the initial contact between with this precursors, but the other surface is not get uniform concentration. So in that case, you will have the very poor deposition on the other kind of this material. So to improve this improve the deposition, so we need to tilt such kind of the system, so that if we pass the air through the air vapor, we will get the uniform kind of the vapor surrounding the material, and then after we'll get a uniform deposition. So in this case, we use such kind of the inductive heater. So this is kind of this made of this graphite, and we can heat this kind of the material using the inductive coil, and based on that we will have the control deposition of the material. So in this particular case, there is no such kind of no kind of the deposition on the surface of the wall. So in this case, we have the only one chamber, and we can just change this kind of the material, maybe the graphite kind of heating material. So or maybe we change here the sample here. So based on that, we can control the deposition of this material. Now let's understand what is effect of pressure. So as we understand from the previous data that here the diffusion of gas is inversely proportional to the total pressure. And here here del G, that Pg upon Pt. So we should not change the concentration on the Pg here, because if we increase the concentration of Pg, so in that case we will get the homogeneous kind of reaction, and that is undesirable. So to get the heterogeneous kind of the reactions, we need to have the PG constant PG pressure that should be very low. So if we have that this one is fixed, the PG is fixed here. So in this case, we have the only one variables, and that is, and so here in this case, we have this variability with the total pressure. So in the total pressure, let's understand what is the effect of the pressures from one ATM pressure if you want to decrease to the one total pressure. So in this case, the Hg is increased by 100-fold. And based on that, we'll get multiple times of the deposition rate as compared to the atmospheric pressure CVT kind of the system. So based on that, let's understand what is the effect of pressure here. So here we have the two kind of the pressure. One is the atmospheric pressure and one is the low pressure. Low pressure, we have the one torr pressure, and that is the 760 torr pressure. So now compare this data at very low temperature. So this is the very low temperature. So if you monitor deposition rate with 1 by temperature, so at very low temperature you have similar deposition rate. But if you increase temperature, what happens here is at atmospheric pressure, so what happens is you will get the very quickly the diffusion control process. So you have the very small reaction control process. Really, that is reaction control process. So for the atmospheric pressure, we have very small range of reaction control process, and after that, there is a change into the diffusion control. So these range is for diffusion control process. Diffusion control, right? But we have some kind of the advantage here. So if we decrease pressure, what is happening here is here the overall the linearity range is increased, and that increase of the reaction control process, right? Reaction control process. So we have the reaction control process at the large temperature range. So at low pressure, we have from very high to the almost intermediate temperature range where we have the reaction control process, and then after we have the diffusion control process. So this region is for the diffusion control process, and if we compare at very high temperature, what is the deposition rate that we will have from here. So there's a many-fold of increase of deposition rate at a 1 torr as compared to the 760 torr pressure, and that is the huge increase in the deposition rate. If you want to deposit quickly material, so in that case we need 1 torr pressure. In that case, we will get the quickly deposition of a thin film of the material. So based on two parameters, one is based on temperature, one is based on the pressure. We can design CVD system, and based on that, we will control what is the rate of deposition of desired material, and based on that, we can control morphology, we can control the crystallinity of the material. So these are the huge advantages in the CVD. So let's understand. So we understand that atmospheric CVD. So that atmospheric CVD has diffusion control process and the slower deposition rate as compares to that at the low temperature, and we compared from the low temperature. So in this case, we have the higher deposition rate as compared to atmospheric pressure CVD. At the same time, we have the larger range of the kinetic control process at the huge temperature range. So that is the advantage of low pressure CVD technique. And here in the low pressure CVD technique, we can design kind of those hot walls reactors, and we can reduce this pressure means long time pass, so scattering effects are the possible, and diffusion length is absorbed, the spaces can be compensated. So these are things you can read. And the one important kind of the CVD is about the plasma enhanced CVD. Okay, my power is very low. Let me connect with the power. Okay. So here we have another kind of technique, that is the plasma enhanced CVD technique. So in this technique, we don't need to heat our sample at very high temperature. So in this particular technique, we can use such kind of the material which are the temperature sensitive. For example, if you want to deposit SiO2 on the aluminum, but the problem is that aluminum cannot work beyond 450 degrees Celsius. So in that case, we need to use the plasma enhanced CVD. So here we can use the plasma techniques to increase the energy of these materials, so that that can come on the surface and gets decomposed easily. So that is the advantage. So using a plasma enhanced technique, we can use such kind of the energy sensitive technique. So here we can add the energy to the reactant using RF kind of the plasma technique, so that that can be decomposed easily. Now, based on the different kind of the energy sources, pressures, precursors, substrate, and the hybrid sources, we have different kind of those chemical vapor deposition techniques. For example, here we have the rapid thermal, we have the hot water. So here in energy system, you have the plasma enhanced CVD, maybe high density plasma. We understand about the pressure based kind of the atmospheric pressure. We have the ultra pressure and ultra high vacuum CVD system. Based on the precursors, metal organic precursors, aerosol assisted CVD, direct liquid injection CVD. Substrate based on this porous kind of this substrate, hybrid physical deposition on the combustible CVD. So based on the kind of energy source you use, the pressure, maybe the precursors, so based on it, we have different kind of chemical vapor deposition. Now, question comes here is that which technique we should use. So for that, so if you have a technical problem that okay, apart from, so among these techniques, which technique I should use. So for that, we need to understand what kind of the things you need. So we have the 5 points. Based on these 5 points, we can choose our desired and the best possible chemical vapor deposition technique. Maybe for that depends on the reactants used in the process, maximum acceptance leak rate for air into the system, purity of the deposit, and size and shape of the substrate, and the process economy. So these are the parameters on which we can choose the best CVD technique for our application. If you want to compare difference between the CVD and PVD, so in PVD we have the highly directional depositions, but in the CVD we have the multi-directional deposition. So we'll get the homogeneous kind of the deposition on all edges here. So here, and the second is non-conformal deposition. However, in a CVD we have the conformal deposition. In PVD, what happens there is, because of the shadowing effect, we don't have deposition in this edge here, right? However, in the CVD, we have the uniformly deposition on the even the hindered area or the edge of the material. And third point is the uses physical process only. Here primarily use the chemical process. And in PVD we are uses the pure source material. Here we can uses the mixed sources materials. It depends on which kind of the materials you need to use. So this is all about the basic uh, theory of CVD. And if you have time, then you go this link and watch the short animation on the CVD. You will get this clear picture about what is happening inside the chamber. And if you want to see the some example how this CVD helps in the in formation of the thin film. So if you want to deposit thin film, so you can use silicon hydride, or maybe you can use the stripe silicon kind of the materials, and based on that you have the different temperature, pressure, or maybe if you have the different kind of the additional gas, and based on that you will get the fine deposition of the silicon. If you want to deposit polysilicon, so for that we will have the silicon, and we have the temperature and pressure, and based on that we will have the polysilicon deposition. Even though we can also deposit silicon nitride, so for that one we can use silane. If you use the ammonia in the carrier gas, so we will have the silicon nitride. And maybe we can use this precursor as well, and put the excess amount of the ammonia in the carrier gas, and we get here silicon nitride. Even though we can deposit silicon dioxide, if you have the silane, and if you put some oxygen in the carrier gas, then we will have the silicon dioxide. So it depends on which kind of the material you want to deposit. And even though if you want to deposit metal, for example, if you want to deposit tungsten, so for that you need to take halide of that tungsten and put the hydrogen gas in the carrier gas, and you will get this pure tungsten coating on this material. And you have the temperature and pressures condition. So these are the applicability of chemical vapor deposition, and this is diverse application of this technique. Or you can modify your technique based on what kind of the material you want to deposit. So this is all about chemical vapor deposition. If you are looking for job in such kind of industry where the thin film is very important, so I recommend you to master the technical skill on the such kind of the decomposition technique, for example, CVD, PVD, asparting technique. So these are very important at the industrial scale. Okay, see you in the next class where we will have discussion on chemical method of nanomaterial synthesis, where we will have discussion about soul gel method. We will have a discussion about hydrothermal technique, sono chemical technique, electrochemical technique. So we will have such kind of discussion, and later on we will have a discussion on the biological system. So we can use the biological template, and based on that we'll develop nanomaterials. So see you in the next class. Thank you.